Our next speaker is Niall O'Dowd, the CEO of Phase3D, and he will be speaking on towards real-time certification with in situ inspection. So, thank you.
Hey everyone, thanks for attending my talk. So I'm the founder and CEO of Phase3D. We're a company that is aiming to develop certification, qualification, in situ technologies for metal powder bed fusion, bioenergetting, any kind of powder-based additive manufacturing. And I'd like to start my talks off with a video and a little engagement. So I'm going to play this video, and we'll see if anyone can identify what's going on in the video. Oops. So does this look familiar to anyone? Does anyone want to take a guess what's going on in the video? Powder, that's true. Got some keyholing here. Got some powder over here. Yep. Particle ejection. Yeah, so it sounds like some people have maybe seen these types of videos before. But this is some data that my team's collected with Argonne National Lab at the Advanced Photon Source using the synchrotron X-ray imaging system that's off the beam line. And it's one of the many technologies and tools that we've been using to validate defect formation during powder bed fusion printing, and in an effort to understand how the powder height of the spread, the powder height of the melted layer, and how many build phenomena come together to create porosity formation. And so in my talk, my thesis, I'm talking about certification, qualification, and I believe that certification really comes as a result of completely understanding the relationship between printing and final properties. And once we understand the complex relationship with all of the different parameters, not just printing parameters, but how the material is deposited, how it's melted, the gas flow and the results, we need all of those relationships understood to promote qualification, born qualified parts, and to certify these components in real time. And so the motivation behind my work is the fact that additive manufacturing is in a pivotal phase. We really see the industry moving from prototyping into production, and a ton of investment in end-use parts from aerospace industry, automotive industry, defense, healthcare, oil and gas, and that's what's really pushing the service bureaus and the printing industry exponentially into growth as we kind of transition in this pivotal phase. But when I think about the future of manufacturing, I think of a fully automated lights-out facility with high throughput, high part quality guarantee. But what we've seen historically, especially in aerospace, there's high scrap rates, and a general lack of agreed upon quality standards means that quality certification needs to be reinvented by every company, every agency, and we see that as really hindering us from getting from the prototyping to full production. But the cool thing is, once we solve these quality and reliability issues, we can have those lights out facilities printing parts on demand with high part quality guarantee, driving us into a manufacturing technology instead of a rapid prototyping technology. And that means, we must collect data from every trial, print, study, publication, program, and the list really goes on. And at first it sounds overwhelming and quite expensive, but to be honest, when we collect the data, it actually produces a method to save cost up front by canceling parts early that we find defects, which are correlated to poor print and final part quality. So basically, as we collect all of this data towards getting certification, we see the immediate gains right away through part rejection early stage. And collecting all of that data in situ is really a way to replace traditional inspection that isn't designed for metal additive. So traditional certification processes that occur after the part is complete really accumulate a ton of lost lead time, a ton of lost cost, and if we can take advantage of all of the digital information that's necessary for additive manufacturing, and also the fact that we have access to all these internal surfaces, we can really reduce the cost and lost lead time, quicken up the iterative loop, and get these parts out with part quality guarantee as they're being printed instead of waiting for the very last stage to do all of the qualification. And so qualification is needed for aerospace to push the industry forward, and as we get there, the cost of a single failure without real-time monitoring can be pretty catastrophic for these thermal heat exchangers that have high post-processing cost, high inspection cost. But when we're able to find that defect immediately, and if we have a high confidence that printing defect will lead to a final part defect, we're really able to drastically reduce the cost of a failed build and get the printer utilization numbers up. And something interesting we see is that there's so much information and scrutiny going into powder characteristics, powder control, powder handling. Part geometry has serious focus. We have a good understanding of overhangs and conformal cooling and all of this AI-generated design. Then we print the part basically with our eyes closed, collect hardly any data about the print, about the part itself, and then we spend thousands of dollars on CT scans, cut-ups, spend years for some additive aerospace components doing post-inspection, looking at density, and it's like, what are we missing during the print? It's like I wouldn't put a roast in the oven for 12 hours and never open the oven to check and see what's going on. And it really presents an opportunity to understand, what did the printer do exactly? You know, I programmed it, it has thousands, hundreds of thousands of vectors. What was the effect of the scan pattern on each layer? Were there any short feeds or protrusions in the build? Did the recoder impact the part? It probably did. Is there lack of fusion defects? You know, we are really missing an opportunity to collect data, part-centric data, not just humidity and temperature data, but part-centric data during the printing process. And our promise, even though all of these models of correlating all of this in situ phenomena and the impact on part quality haven't been developed yet, our promise is that what happens during the print impacts final part quality. It's kind of an obvious statement. But we see that as a massive opportunity to collect and analyze part-centric data to first reduce cost right away, and then build up data lakes and data analytics to help certify and qualify parts in the future. And the cost is so small compared to a CT scan. The build is expensive, the post-processing is expensive. Why not collect part-centric data during the printing process? So that's what we've developed. My company, Phase3D, we released Fringe Research, which is a structured light sensor which measures parts as they're being printed. We identify anomalies during the print process, so researchers, process development, parameter development, scientists, users of AM technology can improve the process. And so it works using structured light. We take a height map of every layer several times per layer, and we report analytics using that point cloud of data. The first scan we do is after the powder is spread. We take a powder measurement. Then after the material is melted, we take a melted measurement, height map. And then we take a third measurement so we can look at the powder layer thickness that's spread across the part, as well as how the part areas are melted down lower into the build. And what we're really excited to share is that we've witnessed a very strong relationship with our fringe research data in situ and porosity formation that we've detected using a CT scan. And so I didn't want to get too technical into all the studies, but we have some major milestones to report from some pretty big contracts that we've been working on for several years with the US Air Force and NASA. So the US Air Force They have thousands of parts on back order. They want to print them. They can print them. The parts look good, but they need a way to prove that the parts are high quality. And so we did this study where we put a challenging geometry part and then a bunch of dog bones into the build. There was rocoder streaks, rocoder hops, spatter, short feeds that impacted our nice parts based on a challenging geometry. And what we found was 100% of the anomalies that we measured in the powder layers, hops and streaks, short feeds, they created pores automatically detected using a CT scan on a dog bone specimen. Meanwhile, we were working with NASA Marshall Space Flight Center. They're printing with GR COP to serve their liquid engines program. And we found a similar magnitude level that was super strongly correlated to anomalies found in the CT. And what's interesting is these are two different printers, they're two different materials, but the one constant is the layer thickness that's designated by the printer. These were both 30 micron layer prints. And so our hypothesis that we're testing next is this 40 to 50 micron range, is that a function of layer thickness? Is that strong correlation and that threshold for when we should cancel a part based on layer thickness? Or how do we establish these thresholds for other materials and make this a repeatable process for any company that wants to predict porosity in the final part? So this is an example of our height map data compared to a visual image, compared to a CT scan from a NASA part. So the visual image, it shows the part. There's some spatter particles in the visual spectrum, or soot particles in the visual spectrum. Our height map is taking analytical data, and we're able to measure, detect, and classify this rocoder blade interaction. Basically, a streak is going through the part, which is creating an anomaly in the powder layer. And amazingly, we saw a streak of porosity in the CT scan data that correlates on the same height as where we saw this layer of the rocoder blade as dragged something over the part. So this kind of data is what was used in the study to get those numbers and to establish that threshold of 42 to 47 micron anomalies are significantly impacting porosity formation in these metal parts. And really we're seeing a big push for certification. The United States Air Force and other DoD bodies, the Department of Energy, NASA has funded us to develop these methods of certification and try to push forward with real-time certification so we can unlock additive to really be printing on demand with a lights-out facility and not take a year to certify a part that may be good, may be bad, but really pushing the industry forward. And so, yeah, thanks a lot for listening to my talk. I appreciate your attendance.
Thank you very much. Questions?
Would your technology work with polymer powder bed fusion as well?
Yes, so it would actually work better with polymer. Imaging reflective surfaces can be difficult. Polymer is much more matte than metal powder. It's just a business case, really. The metal powder bed fusion customers and topic calls, there are a lot more people who have been asking us to develop for powder bed fusion, binder jetting. We're also developing a system for cold spray. I've been wanting to do SLS, but the printing humidity in the chamber and the fogging on the glass and the general lack of ports on the machine compared to the metal 3D printers make it just an engineering challenge. We have done polymer scans on binder jetting, looking at silica with Oak Ridge National Lab. So yeah, it's definitely something that I'm interested in. It's just a matter of staying focused at my small company.
Approximate cost for your system?
Approximate cost, it depends who the customer is. So, no, the approximate cost of...
A really small not-for-profit.
Right. Yeah, so the cost is around $45,000. It's around $30,000 to $45,000 to get started, and then we have a software license. Mm-hmm.
Hi, neat stuff.
Thank you.
How do I put it in my printer without voiding my warranty?
Yeah. So the nice thing about Fringe Research is that it's a very modular system. So we've installed on EOS M290s, DMG Mori systems, GE M2, Aconity systems. We go through light ports or sensor ports. So the EOS M290 has 6 sensor ports on the top. Our camera, the sensor is composed of a camera and a projector, and it can basically be mix and matched as long as there's a degree of separation between them. So we take out a port, an unused port on the machine, we put our camera on. We take an unused port somewhere else, we put the projector on, and we calibrate the system with that geometry.
And they're okay with it?
Yeah. Or you can cut some big holes in the printer, which some people are doing, so.
They will not be okay with that.
That was kind of my question, but I'll add something else then. Can you just explain a little bit? I mean, you have those cool-looking, fluorescent yellow-looking bands. Give us a little mini tutorial on structured light.
Cool. Yeah, so if you can imagine shining some stripes onto a flat wall, the stripes are flat and they look uniform. But if you put some object on the wall like a baseball or something, the stripes deform. And so intuitively you can understand the shape based on the deformation of these patterns. But there are algorithms that get way more analytical and quantitative. So essentially what we're doing is we're encoding a sine wave of light onto the surface. And for every pixel on the surface, there's a phase value that corresponds to the phase of the sine wave. Then something gets put on the surface, and the phase of each pixel changes, spatially forward or back in that sine wave. And then through triangulation, based on the spatial phase difference, we calculate the height from a reference. So we would take a before and after scan, and we know the height difference between the first scan, which is like the datum, and then the second scan, which is like the object.
And is that what it kind of looks like?
Yeah.
When it's actually in your LPBF?
Yes. So this is a fringe on the bottom here. This is a fringe pattern. It looks like a sinusoid stripe pattern that's blurred. Mm-hmm.
Got another question back here.
Hi, thank you for your presentation. My question is about how you compensate. For example, if you see anomaly in a layer, do you actively correct it in the next layer, and how you do that? For example, if you want to implement it in our machine, what we need to change to kind of do those sorts of compensations?
Yeah, so closed loop feedback, closed loop control is a big topic. I see the path to get there in 3 steps. One is measuring anomalies in the build with high confidence. So before you do anything, you have to take accurate measurements that are repeatable and calibrated of the process. That's step 1. The second step is what this presentation is talking about. It's understanding which of those anomalies creates final part defects. How severe do the anomalies need to become to create a final part defect, which are allowable, which are causing porosity formation. Then after that relationship is understood, then it's how do we fix those defects? Because essentially every part has anomalies. We don't want to fix anomalies that are inconsequential on the part quality. We want to fix part defects. And so right now as a company, we've developed this correlation technique to understand which anomalies create defects, and then we're working with printers, printer companies like DMG Mori. They understand the printing parameters. They understand how to tune and tweak the laser, beam shaping, things like that to heal the process. So there's really low-hanging fruit, like a recoat, for example, probably is not too difficult to understand. If there's a short feed, maybe it's one of the stochastic short feeds that happen just because who knows, and then you just recode it. Also, we can do basically zap spatter particles. We can do some beam shaping to try to get the melted surface a little flatter. So those are some examples of low-hanging fruit for closed feedback, but really things get dangerous if we're trying to correct anomalies when we want to correct defects. and understanding the relationship is a first step.
Question in the back?
Yeah, so my question is, you're measuring stuff as it's printing, right?
Yeah.
So is the fact that you're measuring while you're printing affecting your final print?
That's a good question. So we don't add any time to the process. So the interlayer time is whatever you specify it with or without our system. We're using white light measuring a laser powder bed fusion process. So the light doesn't impact the printing process. It's a fully non-contact method of inspection.
Thank you.
Thanks.
Over here, how would you go about correlating whether a problem is a problem?
So
An anomaly is a problem.
Okay.
I mean, so a certain
Yeah.
size anomaly doesn't matter, a certain size does matter. How will you make that determination?
yeah, so the big distinction is between anomalies and defects. We call anomalies the issues that happen during the print, and whether or not it becomes a defect in the part after the part comes out. But like what you were saying, it's all about the customer and the requirements. If I'm printing a tchotchke, I don't care about porosity. And so, but if I'm printing a critical part, of course I care about porosity and probably fatigue and microstructure and everything. So, like aside from the philosophical answer to the question, it's really based on what's the allowable amount of porosity, what's the allowable deviation or fatigue cyclic life, and then once we understand how the anomalies affect that, we can put limits on how many anomalies are allowable. But in general, my background is structural health monitoring, so we talk about like what's defects, and really I think it's related to like general complexity. So if you see like a human-made part, a car or something, a boat, it looks a certain way. Then if you look at a boat that's just completely smashed or a car that's totaled, things are just generally more complex. There's more stuff in there and cracks and more lines and more reflections of light or signals or waves. So I think in general, like what's a defect? When things get really complicated and crunchy kind of stuff like that, I would say.
Where are you located?
We're based in Chicago. Yeah.
Any more questions? Great, thank you very much.